Marketing Manager for Eaton in the UK. And thank you for joining our webinar this afternoon, which is on the topic of arc fault detection devices and forthcoming changes to the IET wiring regulations. So before we start, a little bit about Eaton as a business. So we are a global company, but we're not just an electrical business. We're a power management business that spans across both the electrical sector, but also the aerospace industry, hydraulics, and also the vehicle industries as well. And as well as being a major employer at an international level, we have a really big footprint in the UK, with sites in Slough, Doncaster, Cwmbran, just to mention a few. You may also be familiar with some of our legacy brands in MEM, Bill, Menvir and JSB. And through those brands, safety is something which is at the heart of our business and something really relevant to the webinar that we'll talk about this afternoon. Okay, so the webinar itself, as I mentioned, it's on the topic of arc fault detection devices. It is a CPD accredited webinar. And we hope to send out certificates to support the event within 2 weeks after we've finished the event this afternoon. Okay, so a little bit of a backdrop really to the use of arc fault detection devices. So this year is all about change within the electrical industry. Normally is in a year where we have an update to the wiring regulations. So we'll come back to this sort of topic, but we have the 18th edition of the wiring regulations that will come along in the summer of this year. And that has been planned for some months now, and that was always expected to come into force this year. What wasn't expected was some tragic events that took place in the summer of last year, and that's likely to bring about, or has a strong potential for some further changes within legislation within the UK construction industry. So we have the Morbic report and the Hackett report, to name just 2 investigations that are going on at the moment, and wider investigations also into requirements for safety standards within rented properties in the UK. So we have a year where there was expected to be much change and the potential for even further change that may come along in the near future. So the webinar itself is about arc fault detection technology, but really what we must first of all talk about is a few sort of statistics that sit behind why we might want to consider using that technology. And that's very much centric around building safety and also sort of fire safety within buildings. So we'll first of all talk briefly about some European statistics. We'll then sort of look at the UK and then sort of a few sort of specifics within England itself. So if we look within Europe, the last set of reported statistics from the Fire Safe Europe body indicated that there were 2 million fires across Europe typically each year. 90% of those occurred within buildings. There were 4,000 people that were killed as a result of those fires, 70,000 people that were hospitalised, and the financial consequence of that was 126 billion euros, which equated to about 1% of total European GDP production. And then when we look sort of a little bit closer within those statistics, it was estimated that of those fires, 25% of them actually had their source of it being an electrical fault. So that's the European view. So if we then look a little bit closer home within the UK, just to start with, in the last reported statistics, there was in the region of 200,000 fires that were reported in the UK. Those statistics are then broken down so within England, Scotland, Wales. But if we look within England, we had 38,000 fires that took place within family accommodation, over 1,200 that took place within communal living areas. In the region of 600 fires within hostels and hotels, and as a result of that, there were 346 fatalities within England. So as we'll sort of start to come on to, the industry has and will continue to evolve safety standards and can help to reduce the number of incidents of fire and the number of fatalities as well. And the use of arc fault detection technologies we'll come on to is another layer to improve safety standards within buildings. So when we look at electrical fires, I mentioned before within Europe, 25% of them were estimated to be from an electrical source. If we look within England, the statistics indicate that over the last year that was reported, 29,000 of those did have electricity as a source of ignition. And of those, 8,000 of them was a result where there was a faulty appliance or lead. So that's just some of the statistics as a bit of a backdrop to arc fault technology. Okay, so As I mentioned before, we already have standards, both in terms of installation, also product standards do provide protection against fires. So we look at sort of some of the existing product technologies that exist. In its very sort of simple form, basic format rather, we have or can have insulation of live parts. So that can be through the use of class 2 equipment. It can be cable insulation, or it can be barriers or enclosures to contain electrical equipment. We then have typically some form of fault protection, and typically within final distribution today, that could be miniature circuit breakers or molded case circuit breakers further upstream, or it could be fuse-based technology. And then increase more and more and more over recent years. We then have residual current technology, so that can be sort of sub-distribution or final distribution levels, where that affords another level of fire protection and also personnel protection as well. So the types of faults that this technology does protect against can be overcurrent protection, where there's an excessive load that will take place within the circuit. It can be a short circuit, so that could be through insulation breakdown. It could be a voltage short circuit that takes place. It's typically where you have a large amount of energy and also a large amount of current flow that causes that device to disconnect. And the last type of fault then is an earth fault, where again, through the use of RCDs, we can sort of look to protect against the effects of earth faults within buildings. So that's some of the technology that exists today to provide a layer of protection within buildings. And as we've covered, in its simplest format, that could be a miniature circuit breaker or a fuse, where it's providing some basic fire protection in addition to enclosures. We've seen the growth of RCDs or RCCBs providing an additional layer of protection. And then increasingly within the UK, we see adoption now of RCBOs, where we're starting to combine MCB and RCD technology within a single unit. So we've briefly spoken there about some of the technology that does help to protect buildings and occupants from the risks of fire. There is a threat today where technology within buildings does not provide protection against potential fire risks, and that is through what is referred to as arc faults. And this is where arc fault detection devices start to become more and more relevant. So first of all, what is an arc fault? We can think of it as a micro lightning rather, that can ultimately lead to a fire within a building, and that can be through the breakdown of the fixed infrastructure within the building, so the cables that are already within the building, or it can be through, say, a portable appliance or a lead connected to a portable appliance. And these arc faults are typically not detected by the technology that we use within buildings today, as we'll sort of come on to. So we've covered the types of faults we can get within buildings today that would be detected by an MCB or an RCD. So what are the types of faults that wouldn't be detected by that technology today? So the first type of fault would be a series arc, as you can hopefully see on the screen. That's something where you get a high resistance fault that could occur in series within the live conductor or within the neutral conductor. And the difference here to the examples we showed before is you can still get current flow within the building. It may not be obvious that there's a fault there, but it's a high resistance fault, and as a result of that, it's not a high level of current typically that's produced, but it can be a fault where a large amount of heat is produced and can potentially run away over a period of time. There's also then parallel arc faults that can take place between live and neutral conductors. Again, a high resistance fault typically, where we wouldn't expect an MCB to detect it. And then the third type of fault is between a live conductor and a protective earth, where you could, if it was a fault above, say, typically 30 milliamps, an RCD would disconnect. But again, if it was below the threshold of an RCD, we wouldn't expect existing technology to detect that fault and disconnect. Okay, so why should we consider additional protection? Probably first of all, we mentioned some of the statistics earlier about the risks that exist within buildings today, and the technology doesn't necessarily cater for those risks. But the nature of arc faults is that they are a type of fault, and we'll show some examples shortly, where it's not obvious that the fault is present. It's something as well where the fault can manifest for some months or even years, and can progressively get worse and not be detected by the technology which is typically used within a building today. So we've mentioned the types of faults that can take place. So the next point is, well, how can those types of faults occur? Well, there's a number of different scenarios that can sort of take place. So the first one would be through crushed wires, and we've got a couple of examples up on screen. So that could be crushed wires on portable appliances, where it could be trapped in a doorway. It could be crushed by simply being sort of trod upon. Also, it can be through general wear and tear of appliances, where a lead typically connects to a plug. It could be through impact of the fixed infrastructure of a building, or it could be, as you can see in the third example, where we have a cable being pierced by a drill, say within a wall. That could cause a short circuit, which could cause a device to disconnect, or it could be a small break in the cable, where again you wouldn't see an obvious effect of that, but over a period of time you could get that fault starting to run away. And then the other types of scenarios that could take place, it could be through where you might have some sort of rodent infestation, their cables are damaged, they can continue to conduct electricity, and gradually that insulation is broken down. Or over the passage of time, as an infrastructure of a building ages, you can also get breakdown through circumstances like UV rays and their effects on the cables and the infrastructure of the building as well. So say with arc faults, it's typically faults where they can occur over a much longer period of time, and it's not evident that there was an issue there during that passage of time also. So mention a few potential scenarios. I'm quickly going to talk about now about one real scenario. It's actually from my home. So the example is where for a period of time I had an electric vehicle. If you've had an electric vehicle, you will know that you come with, in my case, I saw it as a temporary charging solution, where it's a 3-pin plug that I plugged into a socket within the garage, waiting for my more permanent charger to arrive. So the scenario that took place was that plug on that charging cable became damaged. So I then rewired that plug, plugged it in overnight, went away and left the car to charge. So unfortunately, what had happened in this particular scenario was that the connections I'd made within the plug itself were not to a suitable standard. Overnight, what that introduced then was an arc fault within the plug itself, and that overheated. And for me, when I came into the garage the next day, the first sign I realised something was wrong was there was quite a distinct smell within the garage, that something untoward was going on with the installation. However, I went to where the car was charging. There was still power to the car. Oops, just step back slightly. 1 second, sorry. So there was still power to the car rather. And as you can actually see within the picture, that socket was still live. It was actually an RCD socket as well. So the RCD socket had not disconnected. And the first point I realized that the fault was actually associated with the car charging was when I removed the plug from that socket, and one of the pins actually remained within the socket itself. So as you can see, it's a real case example where there's an arc fault, a lot of heat generated, but neither the MCBs or the RCD within my consumer unit or the socket itself actually disconnected in the event of that fault. So arc fault detection. So for us as a business, we feel now that this is another level of protection which is relevant within buildings in the UK, and is that extra layer that sits above existing forms of protection within buildings. Okay, so that's a little bit about some statistics, why we might want to consider arc fault devices. We'll come on to the actual technology itself and how that works, but we're just going to now spend some time talking about UK regulations and actually some influences from a little bit further afield as well. So in the summer of this year, we will see the introduction of the 18th edition of the IET wiring regulations. And for the first time, we will see the recommended use of arc fault detection devices. So I should point out that arc fault detection devices and an AFDD, it's not an Eaton term. It's a term that will feature within the UK wiring regulations. It's a generic term. As you know, you might refer to an MCB or an RCD as well. But we're not the first country to consider the use of this technology. So within Europe, there's a number of countries that have started to move towards the use of arc fault detection devices. Within Germany, it's now mandated on certain applications. And then if we look further afield, and we'll come back to this, in Canada and the USA, and particularly within the USA, the use of arc fault detection devices has been used since the late 1990s. We started to be introduced within regulations from 2002 onwards. So there are other countries, if you go onto the internet afterwards, I'll give you some examples where you can learn about the experiences in those countries about adoption of this technology. So coming back to the UK, so I've mentioned before, the 18th edition will come along in July this year and then take full effect in January 2019. I've quickly mentioned I've got Paul Norris with me today, who's one of my colleagues that's quite heavily involved in standards work. So Paul will be helping to answer your questions at the end of this webinar today. But so, as I mentioned, the IT regulations will come into place this year, the 18th edition of it, and this new regulation now, 421.7 rather, will be introduced where there will be a recommendation for the use of arc fault detection devices. So it won't be a mandatory requirement, it will be a recommendation for the use of arc fault detection devices. So where should arc fault detection devices be used? So at the end of the webinar today, we'll share with you a website where you can get a lot more information. It's an Eaton website on arc fault detection devices, about the technology itself, and a little bit more technical information in the form of white papers that you can refer to. I should mention as well, there is a really good guide that's been produced by BEMA, which is sort of a collaboration of different sort of working groups in the UK, that gives some further guidance on the use of arc fault detection devices and its relevance to the UK. And the main sort of applications where this technology is recommended is, first of all, in premises with sleeping accommodation. So typically multiple occupancy dwellings, maybe student accommodation, hotels within that as well. Buildings where there may be an increased risk through the materials that might be stored within them, so where they may be sort of more flammable in nature. Buildings where there can be an increased risk due to the construction of those buildings. And the last one is buildings where they may have some sort of irreplaceable objects that sit within them, so typically museums, libraries, art galleries. So again, there isn't a mandated application for arc fault devices, but there are some buildings where BEMA and within the wiring regulations that it will be suggested that arc fault devices are considered within those building applications. So that's the standards that we will see coming in this year in the UK. We're now going to move on to the actual technology itself and how it works and the formats that arc fault devices can actually come in, because it's not one size that fits all. So, as mentioned previously, arc fault detection technology is something that sits as another layer above current protection and residual current protection that we see within buildings today. And that technology can come in a number of different formats. And there's just a few examples I'll just share with you now. So in its basic format, an arc fault detection device can be a standalone device that just sits on its own, and its pure function is to provide arc fault detection capabilities. It can also be available as an add-on product. So if you imagine today an existing miniature circuit breaker, you will find manufacturers where arc fault detection technology can be available in a format that can be added to that miniature circuit breaker to provide then overcurrent and then also arc fault detection. And the third type then, or fourth type rather, is a type where it's an integrated approach. So if you imagine today, we've got RCBOs where you have overcurrent protection present. You also have residual current protection present. You can also find formats of arc fault detection devices where then arc fault technology is integrated to provide one unit where it is all encompassing and covers all those different types of faults that can occur within buildings. So this is one example. It is an Eaton example. So this is what we refer to as our AFDD Plus. So this is an integrated device, and as the diagram on the hand side demonstrates, it's something where if you look to the left-hand side of the product, it resembles, I guess, a traditional miniature circuit breaker and will provide overload and short circuit protection. It then has residual current protection integrated within it, and then it also has arc fault detection technology integrated within it as well. So if you look at the image on the left-hand side, below the toggles on the device, in this particular case, you'd see some sort of indication about whether there's been, say, an overload or an earth fault that's taken place within the installation. And then on the right-hand side, there's an LED that would indicate whether there's actually been an arc fault within the installation itself. And then in the top left-hand corner, you can probably make out also a test button on the device itself. Um, Testing may be something that we may come onto within questions. So what we'll find is some arc fault devices will constantly test themselves. They will carry out ongoing tests within installation. And in the case of the Eaton product, as well as indicating that there's been a fault within the building, it would also give the installer or the occupant some sort of indication if the technology had sort of prematurely failed, so that indicator of that. For other manufacturers, they may actually provide a manual test button where you would go along periodically and test that product in the same way as we would do an RCD today to make sure it still functions. So in terms of the periods to which to test arc fault devices, the BEMA recommendation is that arc fault detection devices should typically be tested every 6 months. So you will find that some devices, it's a continuous program of testing that will actually take place on the product itself. Okay, so one of the other questions that we actually find that is starting to come up more and more is about, well, have arc fault detection devices that are coming? I think still a really big question about what are they, why were they intended, how are they used, what is the technology? But also the question we find that's been asked over the last few months, well, how does that fit within my existing installation? So we've just tried to provide a couple of examples on screen on how arc fault detection technology could be incorporated within a consumer unit as we move forwards. So the actual connections to the units themselves, it's not dissimilar to an RCD or an RCBO, but what you will most likely find is for most manufacturers there is some form of dedicated buzz bar arrangement that is required. So in the case of Eaton, that would be the case. On the picture on the right-hand side, you can probably make out there's a subtle difference between devices that sit on the right-hand side than those on the left-hand side. So there'll be a dedicated buzz bar arrangement, and that would be, say, typical of most manufacturers. But the actual integration of them within the consumer units themselves is relatively simple, where there would just be an additional feed that's then taken out to those arc fault devices. The other question that we are also, or have been asked over the last few weeks is, well, what circuit should arc fault detection devices be used upon? So there is some guidance, so there is available and forthcoming about the installations where arc fault detection devices are used. The actual circuits they're used upon, what we probably sort of say is that's a risk-based assessment. So you might want to look at the circuits where there is most more risk of mechanical damage to circuits. You might want to look at circuits or applications where they're maybe not going to be tested or accessible more regularly. You might want to consider buildings where you've got occupants maybe changing on a regular basis, or circuits where they're more susceptible to, say, piercing of cables. So typically that might be, say, lighting circuits where you've got vertical drops within walls themselves. So those typically the sort of things that we might want to consider where we're looking at which circuits to use arc fault detection devices upon. So we're now going to talk briefly about how does this technology work. And quite simply, the way the technology works is that it's looking for distortion on the waveforms within the actual infrastructure of the building. So the technology itself is looking for the footprint of the waveform, and there are certain characteristics which the device will look for that it will identify as being an arc fault. The reason for that, and we'll demonstrate on the next slide, is that arcs happen on a regular basis within all installations, probably happening right now in the installation that you're sitting within. So typically, if you operate a light switch, there will be an arc that takes place. If you were operating some sort of rotating machinery, so if it was a drill, for example, there is an arcing that's taking place within that circuit. So with arc fault detection devices, they are designed that they are picking out the specific characteristics rather than arc fault, and ignoring those of a good arc, if you like, that's taking place within a building or within a circuit. It's also worth mentioning as well that certain technologies can exist now within buildings, so particularly power line communications, where they can or have been known to mask issues on circuits. So it's worthwhile asking the question that when you're talking to some manufacturer about arc fault devices, have they been tested to make sure that they are differentiating between what is an arc fault and natural arc, and also have they been tested to take on board considerations like power line products to make sure that when faults do occur, that those characteristics aren't being masked by the use of those types of products. So, arc fault detection devices, just I guess to sort of summarise some of the points that we've sort of gone through, they are available in different formats, and they do now, it's a means now providing this extra layer of protection within a building. Within buildings today, we see overcurrent protection, we see short circuit protection, and we see earth fault protection. But what we don't see today is a means of detecting and actively acting upon the effects of an arc fault. Going back to my earlier point about some of the tragic incidents we've seen in the UK over the last 12 months and also in other countries as well, there's an awful lot of focus at the moment about actually what happened within those buildings. I'm sure a lot of good work will come out about recommendations moving forwards. And a lot of that, when you look at it, is about when a fire occurs, how to prevent a fire taking place, and if, heaven forbid, a fire should take place, how we can mitigate the effects of that fire. Probably one of the most valuable parts of arc fault detection devices is actually it's a really good means of preventing a fire taking place in the first place as a result rather of an electrical fault and an arc fault being the nature of that fault taking place. So it's a preventative means of protection. We've spoken about the technology that's sort of used. So, when you're sort of looking towards arc fault detection technology, it's worthwhile asking the question to make sure that there is this differentiation between an arc fault and naturally occurring arc, and also the technology that's being used increasingly within buildings. That's taken on board when products are tested and examined as well. And then really sort of, I guess, a final sort of point around arc fault technology and its adoption. I mentioned quite early on in the presentation that arc fault technology is new in the UK. It will be recommended for the first time within the 18th edition of the wiring regulations. But I also briefly mentioned earlier that this technology is not new when you look at things on a more international basis. So I think it was as early as 1999 in the USA, regulations there started to look at the use of arc fault technology. In the US, though, although the technology has been used for a number of years now, it's actually recognised as a different name, which is AFCI, which is arc fault current interrupters. So what I would suggest, and it's a really good bit of reading to do, if it's a topic you're really interested in, go away, if you use Google or any other recommended search engine, search on AFCI. There's some really good websites that talk about the experiences in the US and the adoption of this technology. The introduction of the of AFCIs or arc fault devices in the US has been progressive. So I think it was it was looked at in 1999. The rollout then began more formally in 2002. And the reason really that rollout has continued is that there was a study done in 2011 by the National Fire Protection Association. So what their study indicated was a 47,000 fires that they saw in homes in the year they looked at. They believed that 50% of those could be prevented by the use of AFCIs, which is AFDD technology. So we need to consider that in the US, standards are different. The nature of the installations will be different. but it's, it's one example where we can look towards it about the value that was seen within quite a developed country on the adoption of arc fault technology. And when we look at it today within the US, there are 48 states where AFCIs are now mandated within home construction. And I say the reason that rollout has continued is this figure that 50% of home fires could be introduced by the rollout. One of the questions might be around, well, what has the effect been since its rollout? I think I'm right in saying the number of fires in homes in the US over the last 10 years has been reduced by 20%, because the change obviously is brought about as that technology is introduced. We can't say that's solely associated with the introduced of arc fault technology, but I think it's something that certainly is recognised as being, played a really important part of the improved building safety in the US. So I'm certainly encouraging you to go away and look at the use of AFCIs in the States in particular. Okay, so that's a brief overview of arc fault technology, where that sits within pending regulations in the UK. As I mentioned at the start of the presentation, we will be sending out CPD certification to everybody taking part in the webinar today. I would say, my experience over the last few months, even as recently as yesterday, there is still, I think, a lot of discussion, debate, maybe a lack of understanding about the technology in the UK. And that's the reason for wanting to do the webinar today. So we have set up a website where you can get more information from Eaton on arc fault technology. There is some really good video content about how the technology works. There's also some white papers in there where they'll allow you to understand a little bit more about experiences against from other countries. So that website, Chris, who's helping us from Baltimore, is just going to flip to now. So we'll share that link with you afterwards, but certainly definitely encourage you to go there. So that website, if you want to go to it, is eaton.com/livesafeuk. So we'll share that link with you afterwards. Please go on there. If you've got any questions on the back of what you've seen, on the email that we'll send out to provide that website to you, rather, and we'll have my contact details on it. We'd really welcome your feedback on the content that sits on that website. So thank you for taking the time to listen to the presentation this afternoon. I can see there's a number of questions that have come in through the chat as we've been going through the webinar. So I think we're going to open things up to the floor now and bring Paul in to try and start to answer some of those questions.
Okay, thank you. Yes, there have been a number of questions, and we'll take them as we have received them. There's certainly been a question about the and the risk of having an ARC in a UK system. It's particularly to do with Passion's law and the requirement that there needs to be 327 volts to create an ARC, which I'm certainly not going to oppose that by any stretch of the imagination. But the issue here is we're not talking about an arc in free air. We are talking about an arc across a substance which can create a carbonized path. So you actually need a much lower voltage to create an arcing situation within the application that we're talking about. So it's not about a voltage across free air. The next question that came in is concerning testing. At the moment, there are no there isn't any equipment available for functionally testing AFDDs. As you can imagine, to create such equipment would be quite a challenge. It's unlike RCD testing, where you're talking about low levels of current. With an arc fault detection device, to test such a unit, we would need to have a piece of equipment that would literally create either a series and or parallel arc. and that in itself is very much a challenge. There was another question about surge tests and surge requirements, whether there needs to be any protection against surges for AFDDs. The product standard for AFDDs, BSE EN 62606, already includes a level of testing against surges. So there is no requirement to specifically specify surge equipment to protect the product. The next question that came in was about consumer unit fires and the fact that the source of the fires were identified mainly as resistive heating rather than arcing. There was no mention of arcing, and in the main that is the case with the consumer unit fires. And they changed the consumer unit requirements were brought in to stop the spread of fire when there was a high resistance joint within the consumer unit. Some of those fires were caused, or probably caused, by arcing, but yes, the majority were through overheating through thermal effects. But AFDDs are not there to protect consumer units. They are designed and installed to protect downstream installation from the consumer unit. So the installation itself, as in the fixed installation, but also the cabling plugged into socket outlets, so flexible cables, and even down to, in some instances, the actual equipment itself. So it's not about consumer units or consumer unit fires. Another question was about the AFDD combined with an RCBO and a test button. What would the test button do, and would there be a test button? That will be entirely dependent on the manufacturer. As far as the AFDD is concerned, whether there's a test button or not will depend on whether there's automatic testing, which will go on in the background, or there could be a manual test button. And if it's combined with an RCBO or an RCD, then again there will need to be, or there must be, for the RCD portion, a test button. So when it's a combined unit, there will at least be one test button for the RCD portion. There may, that's very possible, that a manufacturer could include a test button for the AFD portion as well, but that is entirely down to the manufacturer. And then the next one was how arcs are detected. How do they work? Do they work on high frequency? And yes, basically yes, they do work on the frequency of the arc. The design of the AFDD is such that it analyzes the signature of the arc and uses algorithms to determine whether the signature is a normal arc through the switching function or a motor operating, or whether it's a dangerous arc that needs to be disconnected and isolating the circuit. Okay. What else have we got? There's a question concerning disconnection times. There are disconnection times stated within the product standard, and they don't vary depending on how they're tested. There's a set of disconnection times depending on the level of arcing current that the device detects. What we got? Oh, sorry, I mean, it's just I can't. I'm going to put my glasses on so I can see better. There we go. Oh, right. there's the question from the question concerning changing the main increment to one fitted with an AFDD. There is no intention that there would be one AFDD protecting the whole installation. The aim is, or the idea is, that the sub-circuits will be protected by individual AFDDs, much as we do now with RCDs. The last thing you want is that if you have an arc fault on a sub-circuit, we don't want the whole installation being isolated. Just looking at the next question from Alex. Split load consumer unit where we see several RCBOs protected by a single standalone device. Again, I think I've just answered that question in that it will always be sub-circuits rather than a single device protecting the whole installation. There's a question about risk assessments, and there will be an element of having to understand the risk involved, because there's no mandatory requirement to fit AFDDs. It is a recommendation. So there will be an element of assessing the risk and the application of the installation. Lifespan of an AFDD, that's not determined in the product standard. And that again will be down to the manufacturer to advise on such an area. But there's no lifespan. There are aging tests within the standard, but no product standard actually dictates a lifespan. After an arc occurs, how quickly can the AFDD trip typically? Again, within the product standard, there are a gradient of trip times depending on the arcing current involved. Protecting the fixed installation, or are most of the faults due to poor appliances or connected cables? It's a mix of both. As you will have seen from the presentation, there is a risk to the fixed installation, where there may be some kind of mechanical damage due to maybe putting a picture up and driving a nail into the cable, or drilling into the cable, but also can be final flexes feeding either extension leads or pieces of equipment, appliances that can be damaged through mechanical damage, animals, pets, anything that can cause damage to the installation. We have to. So in a commercial installation, can you protect the completed distribution board, or is the final circuits only? Again, it's recommended for final circuits only, and the majority of manufacturers will only supply products suitable for final circuits, because we don't want the whole installation being disconnected. The question about the automatic test feature, the test feature operates such that if the device fails, then the device must be opened and cannot be reset. And there's a question about testing during installation testing of a new installation. As with well, in fact, as with most, if not all, electronic equipment, it's recommended that these are disconnected during installation testing.
Just pick up on Bill's question on pricing, Paul.
Yeah, go on.
So we've got a question from Bill on the recommended retail price of an AFDD. I think Bill's asked the question in really, a really good way. So he's absolutely right in that, from our side, that the additional cost. First thing to say is this is new technology. My experience of new technology is that it does come at an incremental cost. it's really difficult to comment in pound note terms on what the incremental cost would be. But as a broad guide, and if you looked at an RCBO today, you would probably be looking at potentially double the price of an RCBO. But what would to say that is today? What we tend to find in new technology is that prices, gradually fall over a period of time as volume increases. But no, that's just as a broad indicator today. But we've mentioned risk-based assessments. Paul did earlier on. So when you're looking at certain applications, I think some of the reports, for instance, last year started to look at this. Cost is certainly a consideration, but it shouldn't mean that we shouldn't use this technology where it is relevant for the application concerned.
Okay, so we've got a question from Mark about AFDDs and use on ring circuits, and suggestion that they cannot protect ring circuits. That's a very good question, actually, because that's not actually the case. They do work on ring circuits. They will detect faults within a ring. There is one area that it will not detect a fault, and that is where there is a series fault within one leg of the ring. The reason for that is that because there is a parallel leg within the ring, then if there's any damage or arcing or risk of arcing in one leg, then the current will actually go down the other leg. So there is actually very little arcing, if any, at all, because of the other current path. Now, in terms of other faults on a ring, if there is a parallel arc, then yes, it would detect a parallel arc within the ring, and it will also detect any series or parallel arcs of equipment plugged into the ring. So if you have a piece of equipment plugged into a socket outlet, and there is a series arc on the piece of flex or a parallel arc, then the AFDD will still detect such arcing. So it's a kind of, yes, they do protect ring circuits, but with a caveat that it does not detect series arcs within the ring itself, because of the parallel path the current can take.
So,
do you want to take the one from Michael?
Yep. So, Michael, a question about the different formats of RCBOs. So, yeah, we showed some examples earlier where it can be a standalone product and it can clip onto an existing protective device, or it can be an all-in-one unit, so it's an extension of an RCBO. So they can vary in size today. We mentioned earlier, it's new technology. New technology, in my experience, does become smaller. The more it's invested in, it tends to become more and more miniaturized. Probably one thing I would mention today, though, is that the size of different devices can have a bearing on their current carrying capacity. So if you found something where it was, say, more compact in terms of its design, you may find that it restricts its current carrying capacity, whereas larger devices may have more comprehensive current carrying capacity. Just something to mention as well is that where you are looking at combined devices, something to consider is that we now have to think about overcurrent protection, or the overcurrent protection they provide, the short circuit breaking capacity, their sensitivity, and then often the arc fault element as well. So just to mention that.
Yeah, if we can pick up the question from Mike concerning making engineers responsible for appliances. That is certainly not the case. Clearly, any installation designer and installer is only responsible for the fixed installation. But these devices do provide protection for appliances that will be plugged into that installation. So we've talked about ring circuits already, so I think we've hopefully answered those questions, and also the size of modules, that's also been answered. Yeah. Anything further?
I'll try to answer Brian's question under the NIC and ECA support the use of AFTDs. will duck my shoulder slightly in that I would probably consult with the ECA and NIC, EIC.
Yeah.
I was actually with the ECA yesterday. I think they certainly have a view on it. I think, you know, the NIC, ECA, other bodies in the UK are providing their members with a number of opportunities to discuss the upcoming change in regulations. I know in the case of the ECA, there was a specific session around art fault technology. So, but for their specific view, I would consult with those bodies is probably the way I would answer that question.
Yeah, and I would add also that they have been involved in the development of the wiring regulations, as have a lot of other organisations. It is a cross-industry development of the regulations, not just down to one or two bodies.
I think we're out of questions at this stage, but I mean, you know, it's been really, really good. We'll stay on for a couple of minutes long in case there are any more questions. I mean, if no other questions come through, I just get to try and close things out. You know, I've really enjoyed this afternoon, genuinely so. We started to talk about this topic probably about 6 to 8 weeks ago now. The reason we've done the session today is, you know, we believe there's still an awful lot of questions in the marketplace about the use of art fault technology. I'd probably go back to where I started with, you know, its introduction into the wiring regulations has been coming for over a year, maybe now, Paul, I guess. There's been sort of ongoing discussion on the use of AFDD.
Oh, yes, yeah,
so,
yeah.
So, you know, it's not, although it's a recent change in terms of its execution, it's not recent around the discussion on its introduction. We have seen events recently, you know, one of you know, the members on the discussion this afternoon mentioned in the chat about the climate has probably changed somewhat in the UK now, which I would agree with. You know, we can't second guess where legislation goes in the future, but, you know, I think there was always going to be an interest in art fault technology. And unfortunately, again, you know, tragic events we've had in the UK means that there's probably even more interest in it than there was previously. I think we should get to a couple more questions that I've seen come through. If you want to quickly cover those off, Paul.
Yeah, yeah, we have a question here from Sean concerning nuisance tripping and detecting whether it's a nuisance tripping or not. Yeah, it's a very good question, and it has been a challenge with RCDs. But you know, if you have an AFDD that is tripping, as with an RCD, then that needs to be investigated and determined, you know, where that arc fault is. Could it be just general nuisance tripping of the AFDD? Well, all I can say is that there is a raft of testing within the product standard to ensure that these devices do not respond to normal arcs through the use of various types of equipment, be it motor-driven, switching of various forms, a whole raft of different types of appliances are used to check that the AFDD does not nuisance trip. A question from Mike about how you know the difference between a self-test failure and an arc fault detection on your device. Well, again, the self-test failure, there'll be, well, certainly with our device, there is an indication as to its condition, but also with the self-testing, it should not be able to switch the unit back on again. Okay, we have another question concerning leakage clamps and ramp testing. Will there be similar tools for the trade? That will, to a certain extent, depend. Right, sorry, we lost audio there, so we're just going to go back to the list of questions so I can pick up on the last few questions. I don't know whether people heard what I said about the self-testing. Where are we? Let me just see. Yes, how will you know the difference between a self-test failure and arc fault detection on your device? As I said earlier, that when there's a self-test, there is a requirement that the device does not switch back on again. So that will stop you from, if it's a normal arc fault, then that needs to be found within the installation. Next question was about RCDs having leakage clamps and a ramp tester. As I mentioned earlier, that it's very difficult to create a test device for such a product due to the need to create, basically creating an ARC. But I'm sure the equipment manufacturers will be looking at that to see whether they can produce a suitable piece of equipment. But right now, there is no such equipment. Would an AFDD trip on a gas discharge? Again, there are tests within the standard with lamps, but I'd have to double check on whether the specific types are tested. So we'll have to take a rain check on that particular one. And harmonics, again, there's a whole raft of EMC testing. There is an incredible amount of testing goes into these products, and EMC testing includes a range of frequencies, voltage levels, surges, sags. There's a whole load of testing that will cover the harmonic side of things. Can they be used on PV car charging? In principle, yes, because you mentioned there about DC voltage current component. That really is more to do with RCDs, and you have to be more careful with RCDs with respect to that. But in principle, there's no reason not to use them on PV and car charging. I'm just trying to think whether, I mean, there are no DC tests as such, but again, if you're obviously on an AC installation, and if there's any arcing, then the device will respond to that. Okay, is there any further?
Right.
Okay, I think we're done.
So we're going to close the webinar now. So just to close things off, thank you everyone again for joining this afternoon. We really, really do appreciate your participation. I've got to make a really big thank you to Paul. I've certainly really enjoyed seeing the answer to your questions, and couldn't have done this afternoon without him. So thank you to Paul. So on the back of the presentation, we will send out a link to the website we've developed. So if you've got a pen to hand, it is eaton.com/LiveSafeUK. So we'll put on the email we'll send out on the back of the webinar this afternoon. And then, as I say, your CPD certificates will be sent to you digitally, which should happen within the next 2 weeks. And then just final point again is my contact details will be on the email that you receive. So if you do have any other sort of questions, please get in contact. And thank you again. If you found it valuable, please share with your colleagues. And we really would welcome feedback. So thank you and enjoy the rest of your afternoon.